Hello, I'm Marikobus, and I'm one of the authors of this poster about stability of loss functions for solar wind forecasting using deep learning, so I'm going to be talking about that. Before I go into the poster itself, I want to contextualize the work we've performed a bit, and then I'll go very quickly about everything in the poster so that it's all as clear as possible, just in case we don't get the chance to talk over the course of the workshop. So we started working on this when we realized we were having some issues having our model converge using mean squared error while trying to forecast solar wind speed using high speed and slow solar wind. So we realized something was odd and decided to take a closer look at the loss functions, and this is the end result of that. So a loss function is very important during a fitting process for a neural network because it can ultimately define the result we get, along with the optimizer and the data we choose and how we choose to use it, as well as the network topology, obviously. So it's one of many components in the problem, but it's one that can directly impact whether the model even manages to converge or not. So it can have a very deep impact on the result. So before we start, we should define what stability means in this context. We say that a loss function is stable if it is resilient in the presence of frequent outliers. This is to say, for any distribution D, we compute the mean and standard deviation, and if there are many values outside the range between the mean minus standard deviation and the mean plus standard deviation, we say that there are very frequent outliers. So stability in this context tells us what to expect if we have that scenario, whether to expect the loss function to behave properly or to lead to issues in the convergence problem as a whole. So I don't think it needs much presenting, but we are going to be talking about the two more commonly used regression loss functions. This is mean squared error and mean absolute error, and we are going to be comparing them. Specifically keeping in mind the individual contribution for any given error value within a batch of size n, which for plotting purposes has been kept to 100, but n can be any natural number that we use as a constant. It will change the actual value we get for any fixed error out of either function, but the behavior of the functions is really the same. It follows the same general tendencies. So we have mean squared error, we have mean absolute error, and we plotted them. The functions are defined in the poster, so there isn't much of a point in talking about their definition. What we find is that, well, first of all, we have even functions, therefore they are symmetric over the y-axis. So we are only plotting the positive side of the range, because the negative side is really the same but mirrored. So we will have them decreasing when approaching zero, and then they increase at the same rate they were decreasing as we move away from zero in the positive direction. So we only plotted for clarity the positive side of things, and we can see that mean squared error and mean absolute error have the same value of the function, the same output. When the error value is 1, they stabilize. This is independent of the value of n, and for values between 0 and 1, or rather between -1 and 1, mean squared error will have a lower value than mean absolute error, whereas for values below -1 and over 1, it will have a higher value, and it will actually increase exponentially. This difference will increase exponentially as we move away from -1 towards minus infinity, or from 1 towards infinity. So this is very important to keep in mind, because this implies a certain curvature, and it implies a certain preference and certain bias in the mean squared error as we get higher values. Now we also confirm this mathematically, looking at the second derivative of each function to study the curvature of the function. Naturally, for the mean absolute error, we get 0, so no curvature. This makes sense because the first derivative is a piecewise function based on the sign of the error. It's basically the sign of the error divided by n. That's the first derivative. By the way, in the physical poster, there is a mistake. It should read sign of the error divided by n. It reads 1 divided by n, probably because it was just found on Saturday before the workshop. So it was fixed. It is fixed on the virtual version of the poster, but it's probably not in the printed version. Just so everyone knows, we got it in time, but not with enough room to spare to actually fix it before it was printed, sadly. But yeah, the first derivative is the sign. For the mean squared error, on the other hand, we find that there is a curvature that's a constant, 2 divided by n, so we depend on the batch size. But other than that, the curvature is constant for the whole function, and that makes sense. Because, yes, the derivative evolves constantly. It makes sense for mean squared error. So what does this imply? Well, as I said before, mean squared error is going to have a tendency to prioritize higher error values and try to compensate for them. This is not necessarily bad, but it can have some issues depending on the distribution of data we have. And to talk about this, what we did was we compared any random distribution and the probability of finding outliers in it with Gaussian distribution, which represents the range of these outliers, pretty much. So if our data distribution is very similar to a Gaussian distribution, the chances of finding outliers are going to be pretty balanced, relatively small compared to the chances of having normal values. And so mean squared error will have no issues with convergence, and it can be perfectly applicable to our problem. If instead we have a heavy tails distribution, whether this heavy tail is located on the smaller or the larger range, mean squared error will also converge, but there is a very good chance that it will bias the model in favor of that tail. So it might lead to a model that has some issues when dealing with values on the opposite end of the distribution to the tail, but this can be perfectly acceptable. In some cases we are interested in those tails, and we don't care so much about values on the opposite end of the spectrum, so we can use it. It's more of a per case basis, it needs to be considered, but it isn't necessarily negative as much as just something to keep in mind while choosing the loss function for our training process. The problem comes when the probability of having outliers on either end of the distribution is roughly the same as the probability of having values within the center of the distribution. In this case, there is a non-zero chance, a non-zero probability that mean squared error will be unable to properly find a correct bias for the model. It will keep trying to bias it in both directions at the same time, and it will be unable to converge. Naturally, it depends on a lot of other things, including the stochastic process involved in determining the initial structure of the network, so it's not guaranteed that it will not converge, but it might not converge, as opposed to the other cases where it will converge and might lead to some suboptimal behaviors, but it can be acceptable. In this case, it might directly not converge, prevent convergence entirely, and this is exactly what happened to us. So you can see the distribution of our data compared to a Gaussian distribution with the same mean and standard deviation plotted in the paper. We describe the case, And that's exactly what happened to us. So empirically, we find it to happen with relative ease in these cases. Actually, it didn't converge a lot more often that it managed to converge when using mean squared error. This was solved immediately by using mean absolute error because it is more resilient to outliers, it is more stable, and so it takes longer to converge, but it converges in these cases. So just as a consideration for the problem of solar wind speed forecasting, yes, if we are not working with separate datasets for high speed and slow solar wind, we probably want to consider whether our data is normally distributed or not. Chances are it won't be normally distributed, and according to the work by Larotera and Sid, it is probably going to be bimodal in its distribution, so that's something to keep in mind when designing the network and when deciding on a loss function. If that's the case, mean squared error, chances are it won't work. So mean absolute error out of these two is probably the way to go in this case, but naturally further work is required to fully determine whether there is a better alternative that we haven't considered yet. There is a good chance that that's the case and we just haven't arrived at it just yet. So that's all. Thank you very much. I hope to talk to you during the workshop. If for some reason we don't get the chance and you have any questions or anything you want to tell me, feel free to email me at mario.cobos@uah.es. My email is listed on the poster, but it is very small, so just saying it. And I'll try to get back to you as soon as possible and provide as good an answer as I can. I obviously don't have all the answers. I wish I did. Thank you very much for your attention and have a very nice day.